Hello everyone, my name is Kan Li, and I'm a research associate at the University of Cambridge. Today, I will give a lecture about the beam bending. This is a fundamental section in the mechanics of materials, but it is a very important consideration in many structural designs and analysis. Beam bending is still actively used in many frontier researches, such as flexible and stretchable electronics, lattice materials, and soft robotics. In this lecture, I will first introduce the basic concept of a beam and the classifications of a beam. Then I will explain the theory of pure bending or simple bending. Then I will show the concepts of the neutral surface or the neutral plane and the neutral axis. Then I will list the assumptions in the bending theory, which is basically the Euler-Bernoulli simple bending theory. After that, I will let you know how to derive the bending stress and the bending strain in a bended beam. Then I will list some examples of applications for the beam bending. Let's start with the basic concept of a beam. So, what is a beam? A beam is a structural member that carries a load which is applied transverse to its length, which is called lateral load. And the beam usually have a length in its longitudinal direction, which is much larger than the other two dimensions. I will give you some examples. The first example is a diving board. When a straight diving board is put there, when the athlete stand on it, the diving board will be bent from a straight shape to a curved shape by these two forces marked here. So this is the first example. A second example is called a simply supported beam. Here a beam is subjected to a load P in the middle, and the beam is put on two supports at its two ends. This is called simply supported beam. How do we classify beams? So the first one is called the simply supported beam, as I just introduced. It has two supports at its two ends and subject to a load or distributed load or anything. And the second one, this is called an overhanging beam. This is similar to the simply supported beam, but its length is extending over its one support in the one end. So this is called overhanging. So if the both ends of the beam is extending over its supports, it is called the double overhang beam. Also, if you have more than two supports, like for here, if you have 5, 6, or 8 supports under the beam, it is called a continuous beam. Also, if you have the beam fixed at one end and adding load at another end or distributed load or anything, this is called a cantilever beam. So how do we classify the reactions in the beam? Let's consider this cantilever beam. So the beam is fixed at one end to the wall, and it is subjected to two forces. One is tension, P, and another is the load, P. So the inner of the beam will generate reaction forces to resist to these outer forces. So this resist will cause three types of forces. The first is tension in its longitudinal axial direction, which is called tension. or compression if in another direction. Another one is shear. So this shear force is transverse to tension, and it is also a linear force. Another one is moment. So this is what we will consider today. So this moment will cause the bending in the beam. So what is bending and what is pure bending? Let's see this panda. It is holding a bamboo in his hands, and the bamboo is bent to a curved shape. So if we look into this bamboo, it is subject to two moments from his hand, from the panda's hand. And if we build a model of this bamboo, we can see it's bending from a straight shape to a curved shape by these two moments. So what is a pure bending? A pure bending means a specific length of the beam, it is subjected to a constant bending moment. But note that there is no shear, no tension or compression in the beam. If there is any shear, any tension, compression, it is not called the pure bending or simple bending. Let's give you an example. Let's consider this double overhanging beam here with two supports A and B and subjected to two loads at the two ends C and D. CA and BD has a length of A. So if we draw the shear force diagram and the bending moment diagram here, we can see that the shear force in the segment AC and BD is not zero. But in the segment AB, there's no shear force. The shear force equals zero. So therefore, the segment AB, it is called pure bending because it has a zero shear force but non-zero moment. However, if we consider the segment CA and BD, it is called non-uniform bending because even has a non-zero bending moment, its shear force is not zero. That is called a non-uniform bending. So let me introduce the concept of a neutral surface or neutral plane. Let's consider a straight beam, a beam subjected to a moment M here, and its undeformed shape is straight. Its cross-section is shown in the right hand. So if we consider the beam is composed by a bunch of fibers or filaments, so which is parallel to each other. When we bend the beam, the top of the beam, the fibers will become shorter, and at the bottom, the fibers will elongate. That means on the top of the beam, it is under compression, and the bottom of the beam, the fibers are under tension. Because these filaments or these fibers are deformed continuously from one end to the other end. So there must be a filament or fiber which undergoes no tension nor no compression. So this fiber, the position of this fiber, we call it the neutral surface or the neutral plane. This neutral surface, even it curves, but please note that its length remains unchanged during this curving. And another concept is the neutral axis. This neutral axis is the line of the intersection of this neutral surface with the cross section. There are a list of assumptions in the pure bending theory. The most important assumption is that the cross-section, which are plane before bending, remain plane after bending. This is the Euler-Brillouin bending theory, which means the plane sections remain plane. This is the most important one. The second is that the maximum stress in the beam is less than the yield stress of the materials. Therefore, the stress distribution can be linear along the cross-section. The third one is that the Young's modulus is a constant in both compression and tension. So this is also for the linear distribution for the stress. Then the material of the beam, should be homogeneous and isotropic, which means it has the same composition and a constant modulus E in all directions. Another one is that the beam should be originally straight and slender, and also any taper must be slight. Another one is that only small deflections are considered here. So how do we derive the bending strain? Let's consider a small segment here of the beam, subject to a bending. So under this pure bending, this straight segment will be curved to an arc shape. So here, let rho, as shown in this left bottom figure, let rho be the radius of the curvature of the neutral axis, and y be the distance between the arbitrary filament from here, the B to B, this arc. This y represents the distance between this filament to the neutral surface. Let's recall the definition of the strain. The strain is a geometrical measure of the deformation, representing the relative displacement between the particles in a material body. The strain is defined as the elongation of the fiber to its original length. So with this said, let's come back to the fiber BB here. The BB has an undeformed length, which equals to the length of the neutral surface, OO, here. It is rho times theta. And after deformation, the length of the BB becomes to rho plus y times theta. Therefore, according to the definition of the strain, we can get the strain in the filament BB here. It is y over rho. Let's put this equation A here and look into it. The strain equals to y over rho. And if we see the component rho here, let's define the curvature kappa, which is kappa equals to 1 over rho. And this curvature can characterize how far the beam is bent. So the equation A becomes epsilon equals to kappa times y. So this is a very important equation. Note that when y equals to 0, it means it is in the neutral surface. According to equation B or A, the epsilon is 0. That means the strain is 0. So this means at the neutral surface, the strain is always 0. Another thing is that when y equals to its maximum, here we define it as C, the strain will get its maximum value, which equals to kappa times C. So the maximum strain always occurs at the top surface or the bottom surface, which is farthest end to its neutral surface. Let me give you an example here. So Let's consider a straight ribbon of uniform thickness T and a uniform width W, and this ribbon is bent into a curved shape by compressing its two ends by 30% of its original length. Knowing that the maximum bending curvature in the ribbon, let's assume that occurs at the top of the ribbon, which is kappa m, and the thickness of the ribbon T, it will not affect the curved shape. So how can we reduce the maximum strain in this ribbon to prevent the material from failure? So let's consider the equation B here. So the equation has a epsilon equals to kappa times y. The maximum strain in this ribbon therefore can be expressed as epsilon m equals to kappa m times T over 2. Here the T over 2 is the maximum Ym here. So therefore the maximum strain can be reduced by reducing the thickness of this ribbon. Since the curvature, the maximum curvature is given. We have introduced how to calculate the strain in the beam. And now let's consider how do we calculate the bending stress in the beam. Again, let's look into this equation B here. So this equation, it only contains the geometric relation. So what if we add the materials constitutive law into it? So let's recall the definition of the stress first. The stress is defined as the force per unit area, which is sigma equals F, which is the force, over A, which is the area. And the Hooke's law gives that the stress sigma equals to E, which is the modulus, times epsilon, which is the strain. And substitution of this Hooke's law into equation B, it then gives the stress distribution of the beam, which is sigma equals to E times kappa times y. And this is shown in the right figure. So this equation C actually shows a linear distribution of the stress at the cross section, which is similar to the strain distribution. So if we look into this equation, at the neutral surface, where y equals 0, it has a zero stress. The sigma is 0. If it is above the neutral surface, where y is negative, the sigma is negative. It means above the neutral surface, the fibers goes into compression. And below the neutral surface, where y is greater than 0, the sigma, the stress is greater than 0. And it means it undergoes tension. So if we consider the static equilibrium equations of this segment, it still has three equations, 3 for force equilibrium and 3 for moment. If we look into the force equilibrium first, so in the x directions, the force equilibrium, the overall force equals 0. And this equation yields that the integral of sigma over the area, it equals 0. Let's substitute this equation C into the above equation, and we will get the integral E y over rho over dA, it equals 0. And then we can get this. We pull E over rho out because it is a constant. Then we will get that the integral y over the area is 0. And this equation indicates that the neutral axis passes through the centroid of the cross section, or the geometric center of the cross section. So this gives us the idea how do we find the neutral surface of the cross-section for arbitrary shape. Let me give you another example here. So how to determine the position of the neutral axis here for this T-shaped cross-section? Again, how do we find the centroid location? It is listed here. Y bar here, which refers to the position of the centroid, and it is given by the integral of y times area it over the total area. So step 1, let's calculate the total area of the cross section. Let's separate this T section into two. One is part A and one is part 2. The part A has area of 1.5 meters squared, and part 2 has a 1 meter squared area. So the total area is 2.5 meters squared. In step 2, let's calculate the sigma YA. According to the reference line which we put at the topmost of the T section, then we will get that the sigma YA, the integral of y over area, it is the 1.875 meter cube here. In step 3, we will find the position of the neutral axis by the ratio of these two. We get the position of the neutral axis. It's located at 0.75 meters. How about the moment equilibrium here? In the direction x and y, we have a total moment of 0, but only in the direction z, the total moment equals to the applied moment, which is me. How about the moment equilibrium? So in the directions x and y, we have a total moment of 0. It's only in the direction z, the total moment equals to the applied moment, which is me here. So this moment equilibrium gives this equation, which is the integral of y times sigma over the area. It equals to me. And if we substitute equation C into this equation, we will get the following equations. Here the me equals to the e over rho times this integral. If we look at this integral, we will find that this is the definition of the moment of inertia. And then we will see that me here, it is a function of e, which is the modulus, and iz, which is the moment of inertia, and the rho. Again, let's change rho into the defined curvature. We'll get the relation between curvature and the moment me. And this equation, we will write it here. This is the relation between the curvature and the moment applied. Here, EIZ here, it is called the bending stiffness, or the flexural rigidity. If we recall equation C here, the sigma equals to E times kappa times Y, we can get the normal stress in the cross section, which is given by sigma equals to ME, which is the applied moment, over IZ, which is the moment of inertia, times Y. So this gives the stress distribution when we know the applied load. So what about the maximum bending stress in the cross section? Again, the maximum normal stress in the cross section locates at the y max, which is the maximum value of y. It can be expressed like this. So let's define here. Let's define Wz, which is Iz over y max. this is defined as the sectional modulus. Then we will have this following equation: sigma max equals to m over wz. So here we note that this sectional modulus, it depends only on the geometry of the cross-section, but not the material properties. So this sectional modulus is very commonly used in the engineering, because if we give a cross-section, we give a sectional modulus of a cross-section, and we give the maximum moment in this beam, we will then get the maximum stress in this beam. Let me give you another example. So if I give you a cross-section of a rectangular shape, how do we calculate the moment of inertia for it? Recall that the moment of inertia is defined by this integral. So with this definition, we can calculate the moment of inertia by this. And for the rectangular shape, the moment of inertia, it equals to bh cubed over 12. Another example is to calculate the moment of inertia for circular cross-section. So here again, the moment of inertia is defined like this integral. So similar to the rectangular cross-section, here, for circular cross-section, we replace dA here, which can be expressed as this. And the moment of inertia, it can be then calculated by this integral, which equals to pi times r4 over 4. Here the r is the radius of the cross section. If we compare the moment of inertia for the same cross section but in different orientations, for example, I put two rectangular shaped cross section here, but one is vertical, one is horizontal. So if we note that these shapes and area are totally the same, the only difference here is the orientation. For the left case, in the previous example, we have got that the moment of inertia Iz equals to bh cubed over 12. And for the right case, we can just switch h and b. We get the similar result, but it is h times b cubed over 12. How about the sectional modulus? So recall the definition of the sectional modulus. Here, Wz equals to Iz over Y max. And for the left case, Iz equals to Bh cubed over 12, and Wz equals to Iz over the Y max, which is the maximum of Y. It is h over 2 here, so it will get Bh squared over 6. And for the right case, it is similar. It is hb squared over 6. If h is greater than b, we will then have the left case has a larger sectional modulus than the right case. Let's consider a complicated case here. So how do we calculate the moment of inertia and the sectional modulus of this cross-section? First, this cross-section, it can be combined by the substitution of the two rectangles. So therefore, we can calculate it in this way. For rectangle 1, we can get the Iz and Wz in the similar way. So as for the rectangle 2. So for the overall final structure, we can simply substitute the moment of inertia of 2 from the left rectangle 1. So we will get this 1 over 12, the capital B, capital H cubed minus BH cubed. Note that we cannot simply substitute the sectional modulus of these two, because it will get the incorrect results. So the correct way is to use the definition, the IZ over the Y max. Here the Y max for the complicated structure, it is capital H over 2. So therefore, we give these final results, WZ here. How to prevent a beam from failure, from the bending failure? Here, again, the maximum bending stress, which is given by the sigma max, equals to the maximum moment over the cross-sectional, the sectional modulus. So this should be less or equal to sigma y. Here the sigma y is the maximum allowable stress, and this is relative to the yield strength of the material. In order to decrease the maximum bending stress, we can consider the following two approaches. The first, according to the equation, we can employ the beam with the higher sectional modulus, Wz. Also, another way is to decrease the maximum moment at max by the overall structural design. Let me give you some examples. And this figure shows some representative cross-sections, and from left to the right, the sectional modulus is increasing. So with the same cross-sectional area, if we want a larger sectional modulus, we can use the I-shaped cross-section here. Let me give you some specific examples here. So let's look into these bamboos here. So bamboo has a very good ability to resist the force of the wind. If we look into the structure of the stem of the bamboo, we can see that its cross-section is a circular ring. So it has a very good ability to resist the force of the wind from bending, because it's a large sectional modulus. And if we look into the microstructures of its stem, we will find that it is combined by a lot of circular rings of its cells. It's called lattice material. So this hierarchical structure gives it a very good ability. Another example is the I-shaped cross-section, which is commonly used in the buildings of our daily lives. So how to decrease the maximum bending stress? This is another approach. So we can decrease the maximum bending moment by overall structural design. Here I'll give you an example here. This is a simply supported beam subject to a uniformly distributed load. So if we draw the bending moment diagram, we can see the maximum bending moment, it is QL squared over 8. So if we arrange the supports in this way, we can reduce the maximum bending moment to QL squared over 40. So the right case have only 20% the maximum bending moment to the left case. So this is a very good example to show how to decrease the maximum bending moment using structural design. Another example is the Wuhan Yangtze River Bridge. This is another example to show the same, to to decrease the maximum bending moment by the structural design, similar to the previous example, but here we're using a continuous beam model. We have over 8 supports here on the bridge to decrease the maximum bending moment. Let's conclude what we learned today. The first important point is that how to calculate the bending stress and bending strain for a beam subject to a bending moment. Here the stress and the strain both subject to a linear distribution, and the stress can be calculated by m over Iz times y, and the strain can be calculated by y over rho or kappa times y. The second point is that how to prevent the beam from failure caused by bending. So the design criteria is to make sure that the maximum stress, the maximum bending stress, is less or equal to the allowable stress. Here again, the definition of the sectional modulus Wz equals to Iz, which is the moment of inertia, over the y max, which is the maximum distance from the top surface or the bottom surface to the neutral surface. The third point is that the design rules to reduce the maximum bending stress. There are two rules. The first is to use a higher sectional modulus Wz, and another approach is to decrease the maximum bending moment by the overall structural design. We need to be very careful here. The sign of the moment here in the previous example, all I chose is the positive, is the smiley face of the beam. So if the beam is bent to a smiley face, it is positive. And if it is bent to a sad face, it is negative. In the previous examples, we have shown that how to prevent a beam from bending. But the bending is sometimes desirable. In some cases, we really want the beam to bend. We want to make use of the bend of the beam or the rivet. For example, here, in the field of flexible and stretchable electronics, we make use of the bending of the beam to fabricate and design the interconnects of the device, and therefore to make the overall device flexible and stretchable. And another good example is that the flexible phone. This one is fabricated by Huawei. So it can have a flexible screen which can survive from bending. Finally, let me give you some sample problems. The first problem here is a cantilever beam. And this cantilever beam is of length L equals to 1 meter. And it is subjected to a distributed uniform load Q equals to 6 kilonewton per meter. The beam is of a cross-section shown in the right figure, which according to the chart has a moment of inertia of Iz equals to 25.6 centimeter to the fourth. Determine the maximum tensile stress and the maximum compressive stress in this beam. So how do we do it? So let's first draw the bending moment diagram. So as shown in the left bottom figure, the distributed load causes a bending moment like this. And the maximum bending moment in this beam, it is QL squared over 2. And we can calculate the maximum bending moment here, which equals to 3000 Newton meter. Note that The bending moment here we calculated is the absolute value, and its sign should be negative because the beam is bent to a set face. Then, after we got the maximum bending moment, we can then calculate it for example for the top surface according to the equation sigma equals to m over I times y. We can get for the top surface, the stress is minus 3000 over Iz times y, which equals to 178 megapascal. And this positive sign here indicates that this is tensile stress. Therefore, the maximum tensile stress is 178 megapascal. And for the bottom surface, this is similar. So again, the maximum bending moment is calculated as minus 3000 Newton meter. And for the bottom surface, we can calculate the stress by m over I times y, which is minus 385 megapascal. And here, the negative sign indicates that this is a compressive stress, and therefore the maximum compressive stress is 385 megapascal. Let me give you the last example. This is an overhanging beam, but with a T-section. And this is showing these figures. And the allowable tensile stress for this beam is 30 megapascal, and the allowable compressive stress, sigma c, which is 160 megapascal. The question is to how to determine if the beam is safe. To solve this problem, we should first determine the cross-section properties. The first step is to determine the position of the neutral axis. This is similar to the previous example we have introduced. We need to find the central location by this equation. So we will get the YC, which is the position of the neutral axis from the top reference axis. It equals to 52 millimeter. And the second, we will need to use this neutral axis to calculate the moment of inertia. So with respect to the neutral axis here, we can calculate Iz, which equals 7.64 plus 10 times to the minus 6 meter to the fourth. Then we will need to draw the bending moment diagram, like the right figure here. We can see that at the point C, it has a maximum bending moment of 2.5 kilonewton times meter, and at point B, it has 4 kilonewton times meter. So then let's first check the cross-section at point B. From the equations, we can calculate the maximum tensile stress here at point B, which is 27.2 megapascal, and this is smaller than the allowable tensile stress. Also, for the maximum compressive stress, we will calculate it as 46.1 megapascal, which is also less than the allowable compressive stress. So we have checked that at the point B, this beam is safe. So how about point C? This is similar, but I'll make this a take-home question. So please check it if it is necessary to check the cross-section at point C. Okay, that is all we have today. Thank you for listening.